for rotating shallow water equations. Very interesting technique. Please.
Thank you to organizer for the invitation. It's a honor to be here. In this talk, after a short motivation, I will review with you the main ingredients of the numerical formulation we are proposing, and then I will show you some results. First on the tangent plane, quite established, the other one on the sphere, that are only preliminary results. We are still working on it. So the framework, our goal is to design a new non-hydrostatic dynamical core for the regional climate model RegCM developed in Trieste by the climate group of ICTP, led by Filippo Giorgi. Here you can see an example of application of this climate model in simulating a dust cloud over Sahara. In this updating of the dynamical core work, I'm collaborating with Dr. Bonaventura and Dr. Estelli in Milan. Well, with this aim in mind, DG methods are very appealing since they have a lot of good properties. But as usual, there is a price to be paid, and nothing is for free. And as you already saw yesterday, for example, if you couple DG methods with explicit time stepping, you will meet severe CFL restrictions like this. P in all this talk will be the polynomial degree. And you can see that if the polynomial degree increases, the CFL restriction becomes stronger and stronger. Moreover, DG methods show an explosion of the number of degree of freedom, so they are more expensive with respect to corresponding continuous Galerkin method. So to circumvent these drawbacks, we mainly use the two ideas. To avoid severe CFL limitation, we couple DG with semi-implicit semi-Lagrangian time stepping. And to contain the computational effort, we equip our discretization with a p-adaptivity strategy. Well, what is new and what is not new in this work? Up to now, DG methods have been already coupled with semi-implicit or semi-Lagrangian technique, but up to now only in a separated way. For example, in this work or also in more recent works, as you saw in previous presentation. Our goal is to couple DG with both of these time stepping technique simultaneously and to write, we call it SI-SL DG method. And then we want to show the viability of the p-adaptivity approach, at least as a complement of the mesh refinement H adaptivity in general, and for us maybe it's more an alternative, since in our model we are required not to touch the mesh, so for us is an alternative. And with this philosophy, we want to solve, of course, the Euler equation to have a non-hydrostatic dynamical core, but for now we are starting with the shallow water equation. We wrote the shallow water equation in general orthogonal coordinates. Maybe why orthogonal? Since again, to be compatible with the model we have to work in, we are required to use long lat coordinates, and so this is the reason of this choice. And so we have also to use structured meshes of quadrilaterals. But I want to stress the fact that the method I'm presenting in the following is not depending by this assumption. So you can extend it also to non-structured meshes and even to non-conforming meshing. Since, of course, thanks to the flexibility of DG methods, you can do it. It's just a matter of more complicated implementation. Another observation, we use here the continuity equation in Eulerian flux form, since we want to be mass conservative, but again, the method could be extended with minor changes to a fully semi-Lagrangian version. And in fact, in parallel to this work, we are also working on a fully semi-Lagrangian version. Well, the first ingredient, the time stepping, it's very standard, the semi-implicit semi-Lagrangian technique, 30-year-old. Essentially, terms responsible for fastest waves are selectively treated implicitly, while the others are treated in an explicit way, and the others here are the advective terms that are recasted in the Lagrangian derivative that is discretized along trajectories. In fact, capital E is the semi-Lagrangian evolution operator. This is the mathematical definition of it, but in practice it means only that you have to trace back the departure points, and then you have to interpolate these departure points. Very standard also this. The space discretization, we start from a tessellation of our domain. We fix in each element of this partition a polynomial degree, and then we look for the solution, the approximation of the solution in these finite dimension subspaces. Notice that elements of these subspaces are only of L2 class globally, not continuous. And this means that we have to define this approximate solution on inter-element boundaries. That means that we have to choose the numerical fluxes. And in this work, we use simple centered fluxes. Again, the lack of global continuity help us in the p-adaptivity, since it simplifies a lot the possibility of a variation of the polynomial degree from one element to the neighboring one. So how to choose the local polynomial degree in an adaptive way? This is the job of the p-adaptivity criterion. Before to describe it, I have to spend a couple of words of the basis we are using to span these subspaces. Well, we are using a modal basis, and since we are working with structured meshes of quadrilaterals, we use as modal basis essentially tensor products of one-dimensional Legendre polynomial. They have good properties, since they give you hierarchical basis, good for adaptivity, and at least in Cartesian geometry, they are also orthogonal. On the sphere, they are not orthogonal as you go closer and closer to the pole. But I show you, for simplicity now, the adaptivity on the Cartesian case. Well, a variable, if you expand it over the basis function, you can compute its L2 norm in this way. This is nothing but the Parseval identity. And in the same way, you can define the contribution to the L2 norm of a function, the contribution coming from a specified modal component. This is the contribution to the total norm of the solution coming from the modal components of degree R. And finally, you can define the weight, the relative weight of this contribution with respect to the total norm of the solution. With these ingredients in mind, I can describe you this very simple adaptivity criterion. So we fix in advance two things. A maximum polynomial degree to be used throughout the computation, and a cutoff tolerance. And then at each time step, what we do to update the polynomial degree is the following. We span all the elements of the partition, and inside each element, we compute the weight of the highest modal component in the current representation of the solution in that element. If this weight is bigger than the fixed cutoff tolerance, then we will add 1 degree of freedom to represent the solution in that element in the next time step. Since this means that in that element, the highest modal component is important. And so we add more degree of freedom to represent the solution there in the next time step. Otherwise, if it's smaller, we decrease the number of degree of freedom to represent the solution in that element in the next time step. And we continue to decrease it until we find a model component whose weight is bigger than the tolerance. This is a very simple criterion, but it's also quite robust. And when if you think to insert a certain point forcing coming from physical parametrization, this doesn't need sophisticated a posteriori error estimates. It's very simple. To finish with the description of the numerical formulation, very standard, we project our equation onto the finite dimensional subspaces. We introduce numerical fluxes and express the velocity degree of freedom from the momentum equation into the continuity equation. And then we get a discrete Helmholtz equation in the free surface elevation only. And in the end, at each time step, we have to solve a linear system, non-symmetric, in the elevation degree of freedom only. And this is the stencil of the linear system we have to solve. Notice that each block has a different size due to the adaptivity, and also this the dimension of this of each block of this stencil changes from not only from one element to the other, but also at each time step. Some results. First, on the plane, here you can see the propagation of a gravity wave. We start from a Gaussian perturbation of the free surface elevation. Here you see the free surface elevation after 10 hours. And here you can see below the distribution of degree of freedom. Each square is an element of the partition. Here there is a measure of the saving of degree of freedom. We just divide at a fixed time step, we just divide the number of degree of freedom used at this time step with adaptivity, and we divide it by the number of degree of freedom associated to maximum polynomial degree everywhere. And you see the evolution of this ratio when the time step evolves. And this is a very rough measure of the error on the celerity. And we repeated this evaluation for increasing Courant number. The same experiment, but with considering also the Earth rotation. Again, we have in the F-plane approximation, we have again the propagation of gravity waves and their reflection on walls, and in the central part of the domain, the development of steady modes in geostrophic equilibrium. And again, below you can see the distribution of the degree of freedom adapted. Here you can see upwards a measure of the geostrophic adjustment process. You see the deviation in the central part from the geostrophic equilibrium, and here the evolution with the time. And we repeated this measure for increasing Courant number. Again, below you can see the saving of the degree of freedom thanks to the adaptivity. The last test in Cartesian geometry is in the beta plane approximation, so we consider the variation of Coriolis parameter with the latitude, and in particular we consider the Stommel model, the simplest Gaussian model. We add the two terms to our equation, the wind stress and linear dissipation term. We are in this box with the side 1,000 kilometers, and this is the solution after 2 months. Notice that we computed this solution at high Courant number, more than 24. You can see the free surface elevation, velocity zonal and meridional, and this is the distribution of degree of freedom after 2 months. Maybe you can appreciate better the dynamic adaptation looking at the solution at as it evolves in time. You can see that in parallel with the development of the Western intensification effect in the solution, you have also Western intensification effect on the degree of freedom. And here on the right, you can see again a measure of the saving of degree of freedom. On the sphere, first the mountain test of Williamson. Here is the resolution we used with, of course, a high Courant number close to the poles. Again, free surface elevation and velocity. Here you can see the same test but with adaptivity. As I mentioned, there is still some problems to be fixed at poles, since there is some noise close to the poles and the adaptivity is feeling it, and you see degree of freedom are excited close to the poles. We don't want this, of course, but we have to fix it in the next time. Williamson test 6 with the same resolution as the previous test. You can see there is still some noise close to the poles. Here is an estimation of the deviation of the angular velocity with respect to the exact solution, but not for shallow water. This is the exact solution for the nonlinear barotropic vorticity equation. And here the test is repeated with adaptivity. The final test I want to show you is a test quite severe for the long lat coordinate choice, since it's the McDonald's and Bates low-I test. You have a flow crossing the poles with low and I at both sides of the poles, and this system is rotating around the pole, and after 10 days you have this solution with the low and I pattern that takes again the initial orientation. To summarize, I presented you a SI-SLDG discretization of shallow water, and I repeat that this is presented on structured meshes, but could be extended also to non-structured, and also non-conforming. For example, to avoid the problems with the poles, we are also considering the possibility to implement it on reduced Gaussian grids. Indeed, we have hanging nodes in this approach, but with the DG is not a problem. And I show you some effects of the p-adaptivity approach in this context, and I show you also some stability properties of the scheme in a non-theoretical way, just considering the maximum Courant number allowed in these simulations. Open issues are the coupling of this scheme with a conservative tracer advection scheme, the parallelization strategy that now becomes mandatory when we pass to the 3D equation, and then a theoretical stability analysis, since, as I told, is not theoretical what I showed you now. What we want to do for the future, open question are to improve the semi-implicit time stepping, since the theta method I showed you is just the basic, most basic solution you can do. We did it as a first step. And also the preconditioning is quite important. I don't know if I told you, but we just used a very naive diagonal preconditioning. And for sure in 3D we have to to introduce something more suitable. But even with so naive preconditioning, it's working so in an acceptable way, also the number of GMRS iteration. And finally, we have to arrive to apply the same philosophy to the Euler equation to have a non-hydrostatic dynamical core. Thank you. This is all.
Any questions? Yes, Brian.
Ronnie, the Helmholtz operator that you have
Yes.
for your semi-implicit problem, do you have it both on a sphere and on a plane?
Yes.
Is it, so you're able to construct that Helmholtz operator because of your center fluxes that you choose?
Excuse me?
Is the fact that you can construct a Helmholtz operator
Yes.
tied to your choice of the center fluxes?
Yes.
And that's stable?
Yes. Maybe. Yes. You are wondering why it's stable even if I'm using central fluxes. Yes. The point is that I didn't enter in details, but if we use a centered fluxes, but for example, in the definition of the discrete gradient operator, we are using a double integration by parts. And in this way, you can recast the flux terms in terms of the jump of the solution. And so, yes, it's true that we are using centered fluxes, but we are taking care also of the jumps of the solution. Maybe this is one reason for which we are stable even using centered fluxes.
I'm just surprised that it's stable either way.
Any questions? Okay.
Are you planning to use a global model for regional climate modeling then?
Well, but for sure, since we are developing a new scheme, we have to test it on standard tests, Williamson tests are on the sphere. For sure, in our climate model won't be used in also close to the poles, since the physics of the poles is not planned to be used in this model. But of course, in this phase, we want to test at least for testing in global version. And moreover, it could be interesting to, in a sort of HP adaptivity, to use it in global version, in global way, to produce a boundary condition, and then to zoom on the regional scale.
Have a regional version also.
Excuse me?
You'll have a regional version also.
Yes.
Uh-huh.
Okay.
So, but will you stick to the tensor product basis even if you're dealing with 3 dimensions?
Yes.
Okay. Will become expensive, I think.
Yes, probably yes. Also, this is quite expensive, but
Okay, Nick.
Giovanni, if I've understood correctly, I think you're discretizing your continuity equation using an Eulerian flux scheme that's handled semi-implicitly.
yes.
So that's similar to what we do, and what I think is going on there is that the large Courant numbers near the pole, that is going to slow down the advection of your mass field compared with the semi-Lagrangian advection you're using elsewhere. And I'm wondering whether that's contributing to some of the noise you see near the poles.
This could be a reason, yes. We could check better in this direction now in the next days to, yes, thank you.
Okay. Any questions? Okay, I have a question.
Maybe
So-
more than one.
No, I'm very curious. Do you have any result with the cross-polar advection? Something, you are using Lagrangian grid, anything crossing over the pole. Did you do some kind of experiment?
But yes, we made, but for example, the test 2 of Williamson with alpha equal to pi half pi. You have and yes, we of course before to do this test we did that test, and we noticed that problem of some noise at poles.
Yeah, at the pole you get triangular cells. Is that correct? At the pole, nearby the pole.
Yes, since at poles the metric factor of the horizontal side at pole are 0, so in abstract in lat long domain are squares, but due to the metric factors they are like triangles.
So your element is triangular shape. Physical element is in triangular
Yes.
shape. So how do you do your discretization then? Then you have a mixed method.
No, but we are using all the integrals are computed in in the coordinate space.
Okay.
And then in all integrals, we have the metric factors. So we compute only integrals on quadrilaterals.
Oh,
And then the contribution of the side integral contain a metric factor, and this manages automatically the fact that at poles the quadrilateral transform itself in a triangle.
okay. I have one more question. It's the last question. How efficient is your semi-Lagrangian semi-implicit in comparison with the explicit method? Did you make any comparison?
No, not yet. Not yet.
So, still, what do you expect? Maybe 2 times, 3 times
With respect to the
explicit time stepping, if you use that one.
with the explicit time stepping, I suppose, according to the results you showed yesterday, so we have we can afford the time step very large. Of course, we pay a price.
For
This
the-
is the price we are paying.
Helmholtz solver, you have to solve,
Yes,
That's
this probably one DG guy, classical DG guy, are telling me, but okay, you can afford a big delta T, but you are brutalizing DG with this stance. Since
One more thing.
this is the price we are paying. We know.
One more thing. Big delta T is not a good attraction if you have parallel communication with semi-Lagrangian method. Your upstream points of cell can be far away from a point.
Yes.
So,
Yes.
it can really kill the communication.
Yes.
To some.
Yes.
Okay, thank you very much. Very nice talk.